All right, so I thought it might be fun just to kind of go through how to solve this gold rush problem using dynamic programming. So the challenge here is, can we get it? Can we solve it using dynamic programming? And I think a personal challenge is, can I do this in less than 30 minutes? That's probably harder to do than solve this problem using DP. So what do we got here? Well, we've got the gold rush problem, and it's reinstated as the rod problem or the rod optimization problem, but generally the idea is that you've got some rod, if you've got something of some length and you want to sell it, right? And someone comes to you and says, I'll buy that, but here's a bunch of prices that I'll give you a bunch of prices depending on the length. So let's just have a little bit of a look. We can see here that, for example, if the length of the rod that you have is 8, someone comes and says, hey, look, here's some prices depending on the length. So if you give me a rod of, say, 1 centimeter, give me a bar of 1 centimeter, I'll give you back $1. But if you give me a length of 2, I'll give you $5. So you can kind of see that it's not uniform. There's going to be some combination of the cutting the bar up. It's going to yield a higher price. And so in this case here, the maximum attainable value is $22, right? Because we could cut it into a length of 2 and a length of 6 and get 17 and 5, as opposed to just handing over the rod of 8 and get 20. So we want to know, you give me a rod, and I look at the prices, and I'm going to work out what's the most optimal way to cut up the rod. And we're going to go and implement this function here. So I've loaded up a REPL here, and what we're going to do is we're going to think about, how do we go about solving this? Now, whenever we have kind of problems with dynamic programming, the first kind of thing to think of is, okay, how would I solve this using brute force? And brute force is simply the idea of just try and generate every possible solution to the problem, and then just keep track of which one's the best one that you've seen, and then return that. So it's slow, but you kind of have this nice property that you've seen all possible answers. So you know, for sure, which one is the best. But even if, okay, cool, I'm going to try brute force, you've got to start thinking well, what's the best, or rather, what does the solution look like? No good if, you want to do brute force and you want to check each, possible solution if you don't quite know yet what a solution would look like. Now in this case, we're given rod length and prices, and we want to know, given those two things, how should I break this rod such that it yields the highest price? And we can think of rod length as just a number, right? Because it is. You just get past an integer. But we can think of, instead of thinking of the rod length as representing some rod, we can think of it just representing a number, right? It's just some number. And what we're going to do is we're going to work out how many ways can we break up this number. So if the rod length, for example, was 4, all the ways to break up the number 4 would be 1 plus 1 plus 1 plus 1, or rather, let's just start with 4, right? You can just not break it up, or you can break it up into 3 plus 1, or you could say 2 plus 2, or you could say 1 plus 1 plus 2, or you could say 1 plus 1 plus 1 plus 1. All these sum up to 4, right? That's 4, that's 4. And so if I returned you, right, 1 plus 1 plus 1 plus 1, you would know, oh, okay, what I need to do is I need to cut the rod up into 4 pieces of size 1. Or in this case, I need to cut the rod up into first a size 3 and then into a size 1. So that's good. But what we're going to say is, I don't really want to turn you a string representing this kind of, summation. So instead, we're just going to return an array representing, each item in this sum. So we'll say, in the case that you need to break up into 3 and 1, we'll just return an array saying 3 and 1. And you can kind of look at this as first cut into length 3, and then cut it into length 1. And so here would be 2, 2, and here's 1, 1, 2, and 1, 1, 1, right? So you can kind of think of like if I was to give you the rod length and the prices, I'd expect to see for you to give me back one of these arrays, right? One of these, for length 4, this is the solution space, right? It has to be one of these. One of these will be correct. And that's the kind of idea, right? If there was a way that we could generate all of these arrays, then we could just check each of these array and say, oh, what price do you get, right? So we could say, what price do you get? What price do you get? What price do you get? And then just work out which one gave us the best price and return that. So this game of kind of breaking up an integer into, the sums of small integers is known as an integer partition. So we would say that 3 plus 1 is a partition of 4, and 2 plus 2 is a partition of 4. And so what we really want, it'd be great if we had some function that we gave it the rod length and then it gave us back an array of all these partitions. Then we could just iterate over each partition and we could just keep track of which one gave us the best price. Now, it turns out that it's actually easier to compute integer combinations than partitions. And all the combination says that in the case of a partition, 1 plus 1 plus 2, right, is the same as 2 plus 1 plus 1, right? A partition would say, well, no, I'm the same partition. Whereas if we think about integer combinations, 1 plus 1 plus 2 is different to 2 plus 1 plus 1. So order matters, in terms of you think about the array, order will matter for a combination. And what we're going to do is, it turns out it's easier to compute the combinations than the partitions. So we're going to first define a function that kind of can give us all these combinations. So, all right, so I think we've got an idea now on, the solution space. So now we've got to think like, all right, the general idea here is we're going to define a function called BruteForce that takes the rod length and the prices, and it's going to give us back, in the case of when rod length's 4, it's going to give us back one of these arrays. So what we want to do is we want to kind of say, combinations equals integer combinations on rod length. And then like 4 combination in combinations. Now we haven't defined integer combinations, but let's just imagine it's there. Let's imagine we had a function that can give us an array of arrays representing the combinations for some number of that length. So we're going to say for, what are we going to do here? Const combination in, and that's probably needed to be of combinations. We're going to have what are we going to say? Max price. And we're going to just set it to negative infinity, because if you can't beat negative infinity, then you probably should hold on to the gold. So we're here, we've got, we're going to start, our original max price is going to be negative infinity, and the idea is we're going to try and find one of these combinations that has a better price than negative infinity. So I've defined a function called price4, which just takes a combination and the prices and just returns us the price you would get if you were to, sell. Basically, all it does is just reduces over the, reduce over the combination. And so basically, if it sees something like 1, 2, 3, it would basically just say, what price can I get for 1? And this kind of translates to, if you did price for that, you can kind of think of that as saying, what's the price for the price of cutting into 1 plus the price of cutting into 2 plus the price of cutting into 3. So that's all it does. It just given a combination returns what price you would get for that particular combination. So we say price for this combination. And what we're going to do is we're going to say max price is either the current max price or the price that we get for the combination. And then we can just return the max price. So that's the brute force implementation in a nutshell, right? But we've got to define this integer combinations. That's the brunt. That's doing the most of the work in this in the brute force solution. So let's go and define that. So it takes some integer n, right? And the idea is going to break it down into a list of integers. So it's going to, like we said, if you give me integer combinations of 4, then that should return, this kind of, you can kind of think of it like, okay, here, integer combinations of 4, it should return 4, 3, 1, 2, 2, 1, 1, 2, 1, 1, 1, 1. And I mean, we know that it should also give us 3. If I break this down to a new line. Let me try this again. So what should this integer combinations return? And like we said, it just returns all possible combinations for some integer n. So let's say if I called it for 3, I'd expect that this would give me back 3, right? Not doing anything. 2 plus 1. Likewise, 1 plus 2, because like we said, order matters for a combination. And then 1 plus 1 plus 1. So that's kind of what we would expect for 3. So if we think about it, what we can say is, we know there's a base case, right? So we're going to do this recursively, and the base case is if n equals 0, what are we going to return? So how many ways can you combine 0? Now, intuitively, it feels like it's an empty array, right? We've got to return something, and it seems like an empty array makes the most sense. So let's do that. The next thing we do is we want to say, well, okay, integer combinations. I can think of it like this, right? I can say, well, if I have some integer 3, what I'm going to do is I'm going to take 1 out, and then I want to know how many ways can you combine 2? And then for each way you can combine 2, I'm going to add 1 to that list. So what I mean by that is, basically we can say something like this. If I want to work out 3, I can say, well, that's kind of equal to 1 plus all the ways I can do it for 2, and 2 plus all the ways I can do it for 1, and 3 plus all the ways I can do it for 0. Right? And so if you think about it, you could say, well, integer combination 0 is an empty array. And then that would mean like, okay, cool. Integer combinations, well, actually, sorry, let's go back. So that's kind of, yeah, so integer combinations for 0 is an empty array, right? Just because we defined it here. And then integer combinations of 1, well, we know that would look like this, we would know that that's an array with the one way that you can combine a 1, which is just 1 itself. And so then we would say, and then for 2, well, you could have 2, or you could have 1 and 1. And so here, this is the integer combinations for 2. We can say, well, what we really want to say is, we want to add 1 to each of those arrays. So now we kind of remove this 1, but here, this is integer combinations for 1, but that we can't return that because that doesn't equal 3. So we can say, like, we kind of want to get this 2 into here. That was good. And then this 3, well, that was an empty array, so we kind of want the 3 into there. And so we kind of want to like kind of just add, integer combinations for 3 is kind of the concatenation of all these arrays. So that's kind of how you can think about solving this problem. And so what we'll say is we'll use that range function we defined, which given some integer or given some number, two numbers, it will create like an array from, the start till the end, inclusive. So what we really want to say, to kind of capture this idea before, which was, 2, so rather 1 plus 2, 2, 3, 2, 1, 0. To capture this idea, we're going to say we're going to start at 1, and we're going to iterate up to 3. So we're going to map over that and get I out. And then we're going to say, well, we're going to call integer combinations on 2, right? And so 2 is going to be our n minus our I, right? N here is 3, I is 1, so this will be 2. So we'll say n minus I. And then for each of these combinations, we kind of want to add the, I. We want to add I to the result. So now you want to say, well, I want to return integer combinations.map, right? And what I want to do is I want to grab the combination, and I just want to return I appended to the combination. Now, the problem here is this is going to be nested, right? Because here we're returning integer combinations returns an array, right? So now we're going to have integer combinations as an array, and we're returning an array. So we kind of have to like flatten this structure, and we can use flatmap to do exactly that. So now flatmap will take each of these arrays, and we'll kind of combine it up such that the return result is just, a two-dimensional array. It's an array of arrays, but each array is one of the partitions, or the combinations rather. So it looks like we've got it, right? We've got integer combinations. And so we expect that we should be good to go. So let's give that a 12. So I'll pull the console up. And I've got a function here called test solution, and that just did not like that at all. We've got, one thing that's not going to help us is we've got 1 and 3 hard-coded, which is really what we want to say here. We want to go from 1 to n. Oh. Okay, so what we didn't do is we didn't, no good calling range and never returning it. So did all that hard work and never got returned. So let's have a look. We can say integer combinations. 1, that looks good. 2, that looks good. So if I give you 3, I can give you 1, 1, 1, 1, 2, 2, 1, and 3. So that looks good. So it turns out that math.infinity isn't a thing. It's just infinity. So that kind of explains this kind of weirdness that we're getting. So now, cool. So we've got negative infinity. So just before we run this, it might be worth also just capturing which partition was the best, not just what was the best price. So let's go let best combination equal an empty array, and then we'll just say we'll just move this into price, and then we'll say if price is greater than max price, then max price equals price, and then we're going to get a handle of that combination. So we're going to say, yes, the best combination is the one we're just looking at. It's this one just here. And we'll return an object of max price and the best combination. So now we can just see what it actually thought was the best combination when we run the tests. Much better. So we got, for the first one we got max price of 10, and the best combination you could find was if we just cut it up into 5 pieces of length 1, and the same thing for the second comment for rod length of 3. And so if we kind of go down to our test and have a look, so for this one, we got best price was 10, and that was if you had 5 pieces of length 1. And so that you can say that if we had just kept it as 5, we would have only got $2. Now for length 3, if we just kept it as 3, we would have got $5. But it worked out that, hey, if you actually break it up into 3 pieces of length 1, you can get $2 for each of those pieces. And that's actually better than what you could get with any other combination. So this looks like it's doing the right thing. So you might think, hey, that's long enough. Let's call it a day. I've given you a brute force solution. That should be plenty to go ahead and solve the problem. And that'll work fine for small numbers of, if your rod length is small, this is actually not a bad way to solve it. It's going to be quick enough. But what if we had rod lengths of 100 or 200 or 300? This won't cut it, and we'll see why if we were to even just say, comment out this test case and say bump this up to even just 20. I just want a rod length of length 20. What's the best way to compute that? And would see that if I run that, so I'm just going to comment out this. All right, so I'm going to run the test, and we're going to run the test of rod length about length 20, and we'll see here that the REPL will just hang. All right, it returned. So hey, it returned. It's good. Got a result, and it said, well, if you've got length 20, the best way is to basically the most you can get is 40, and that's just breaking it up into 20 pieces of length 1. So I go, hey, 20 is not too bad. Well, what about if I wanted to know 30? So I go, okay, cool, and this is pretty similar. So we've just restarted that, and if I run tests, what am I doing that for? All right, so this is we're just going to run now. So instead of 20, we're going to have a length of 30 and see how we go. Alrighty, so no good. So we just ran out of memory, right? The REPL just came out and said, hey, sorry, we have to stop running your node process because you just ran out of memory. And the reason it ran out of memory is because it had to go and create, if you remember, integer combinations, has to go and generate all possible combinations for the integer of length n, and in this case n is 30. So it's going off and it's just generating all these arrays which represent all the ways you can combine 30. And it goes, I haven't got enough memory to store all those arrays. Now we actually can solve this problem by using generators. We just yield the result one at a time, and so we kind of have constant space in the sense of we can, instead of building all possible arrays and then handing over to our brute force, we could kind of yield a value and then a new value and then a new value, and kind of don't need to kind of wait. But it's still going to take forever. It's going to take so long. So this is kind of where at this point we haven't even touched dynamic programming. We're just talking about how would we solve this with brute force. And so dynamic programming takes this problem, right? And this problem right now is exponential in time, right? It's 2 to the n. If you think about, if I give you a rod length of 10, and then I want to give you a rod length of 11, right? I have to do twice the amount of work, right? I have to do twice the amount of work to do 11 compared to 10, and then 12 is going to be twice the amount of work of 11. So very quickly it gets out of hand, and we're waiting for centuries for it to finish computing. So this is great. We're pretty confident that the brute force solution is working, but And it's great that we've got this, because now we can think, all right, if I can implement it another way, I can just compare what brute force gives me to another solution that we come up with. So we can kind of have this now as like our checkup. We can always check our new solution against brute force to see if we're correct. So where do we start? So let's define a function called dynamic for our first attempt at the dynamic programming version. And it's the same thing. It takes a rod length. I cannot spell today. And it takes prices. And the idea is the same thing. So now we've got to think about, like, what does it mean to be, okay, great, I've got the brute force, but, how do I think about, working out how to define this using dynamic programming? And if you remember, dynamic programming is just about recurrence relations, right? It's about how would I define this problem or describe this problem recursively. And if we think about it, if we take that example of our rod of bar length 4, what we're really saying is we can say, you know what, like, how can we solve this problem such that we can, like, think about, another way of saying this is that essentially, to get the recurrence relation, or to think of a recursion, we've got to think of, like, well, how can we describe the problem such that we can, like, break it up into small sub-problems? We want to, like, do some work and then, like, call ourselves recursively and do the rest of the work. And if we think of our bar of just this, like, these 4 dashes representing a bar of length 4, what we can say is we can say, you know what? Let's just imagine we cut it at the first kind of, index. And then we say, well, I know how to price that 1, the length 1, and then just tell me what's the best you can do for length 3. And then I'll just add those prices together. And likewise, then I could say, all right, I'll break it into 2 even pieces of 2, and I'll see what I can get for 2, and then tell me what's the best I can get for 2, right? I'm going to, like, recursively call myself and ask what's the best I can get for 2. And then I can say, all right, I'll cut it, into 3, and then I'll see what's the best I can get for 1, right? And then add those together. And then I'll cut it into, like, 4 and 0. I know how to price 4. I know how to get a price for 4. And then I'll get the best for 0, which in this case is nothing. So in other words, what we're saying is, what we really want to say is, I want the price. If you give me some rod length of 4, well, I can say, you know what? I know how to get the price for 1, and then I want to get the price. So we take, like, dynamic here. So you could say the dynamic solution for 4, and let's call this, like, optimal best price. The workshop there. So we'll say the best price of rod length 4 is going to be the price we get for 1 and the best price we get for 3, right? Or 4 minus 1, which equals 3. And then we can say, all right, and then we can say, well, I'll now get the price for 2, and now I want to know what's the best I can get for the remainder, which is 2. And then I'll say, all right, then I'll take the first 3 and see what I can get, what's the best price I can get for the rest. And then lastly, I'll just see what can I get for 4, and then I'll see what I can get for the rest. And when the rest is 0, I can just get 0. So we can kind of think of it recursively like this. And the best price is going to be kind of like the max of what we get for, where are we? No, conceptually we can think of it like this. The best price for 4 will be the max price we can get for one of these. Right? And so that's it. That's our recursive definition for the problem. And so we can kind of, take that kind of example and kind of now just, generalize it to, instead of best price of 4, we can say best price of n, and we can see that we would go from 1 to n, and then we would calculate the rest, the remainder of the rod. And so it kind of has a similar structure to the integer combinations, funnily enough. But if you think about, right, cool, best price, what's the recursive case, what's the base case, right? So in the case where the rod length is 0, we would need to return something, right? Now we were saying, what's the best price you can get for 0? Well, it has to be 0. You know, if you give me a rod length of 0, I'm giving you $0 back. Doesn't matter what day of the week it is. It doesn't matter if it's your birthday, right? I'm giving you 0 for a rod length of 0. So now you think of the recursive case. Now you kind of want to do this bit here, right? We want to say like, well, I want to like iterate from 1 to n, where in the case where n is 4, the rod length is 4, we're going to go from 1 to 4. So I want to say, well, I want to have a range, a list from 1 to n, and for each integer in that list, right? So if rod length was 4, 1 to 4, this would return, you know, an array of, you know, 1, 2, 3, 4 for these integers here. And then for each integer, I want to find out what's the price for it plus what's the best price for the remainder. So I want to look what's the price I can get for I. And remember, it might not be in there. So if it's not in there, then we're going to have to, what am I doing? Where am I? I'm back. Yeah, so if it's not in there, now we're not guaranteed that it's in there. So we have to also have a default value, which is going to be 0, right? And then we want to say that's plus the best price of the remainder, which in this case will be n minus I. And so we can kind of say that this is going to be, now, this is going to return an array of the prices, where if you cut it at each kind of, you know, interval or each like kind of possible place along the rod, this is what you would get. Right, so you can kind of think of this as like, this is the best prices, you know, at each cut. Right? And all we want to do is we want to now just do this max part where we say, all right, well, we'll just return, you know, the max, and we'll just spread the prices, and away we go. So if you think about now, right, let's just log out best prices at each cut. And this kind of, that's it. We're done. We just need to return this value, and that's good to go. Best price 4, got 1, 2, 3, 2, 4, 1. And so you can see all the recursive calls, right? When we have rod length of 1, it says best. It basically said, okay, I'm going to look and I see that I can cut it just I had the one option, right? I can just cut it into length 1. I get 2 for that. And then rod length 2 says, well, there's 2 ways to cut a rod length of 2, right? 1 plus 1 or 2. And so for each of those options, right, there is some value. So in the case of, it looks like for 1 plus 1, right, in 2 equal lengths of 1, we say we can get 2 for each piece of 1. But because we haven't defined a value or price for length 2, the case where you went to just 2 by itself, just a length of 2, you get nothing. So it looks like it's doing the right thing. And so now, if we come down and we just comment that out, we could say, all right, well, let's go to our tests. And what we want to do is we just want to compare the brute force to what we get for our best price. So best price, rod length, and then we'll call best price. So now if we run all our tests, let's see if our recursive solution, right, is equivalent to the brute force solution. So we saw here that we got 8, that's good. And so for 3, it gave us 6, and our best price gave 6 as well. For log length of 2, it gave max price is 4, we got 4 as well. 22, 22, 24, 24. So it looks like our implementation is correct, right? It looks like our recursive solution is equivalent to our brute force solution. Now we saw before with our brute force solution that when we caught it with a rod length of 20, right, it took a while, but it eventually gave us a result. And I think it said just to cut everything into 20 even rod bars of size 1. So we would expect, right, let's kind of just see what we get for our recursive solution. Right, so pass in 20 and some prices, and we'll see what we get. $40. Okay, cool. So it returned 40, and I'm pretty sure the brute force did the exact same thing. And so it was quicker, but it was still a little slow, right? It was still a little bit slow. And if we think about it, like if we call best price on so we're happy with this, right? We think, okay, cool. All right, this is, sweet. We got, it was a bit faster. It wasn't heaps faster. But what if we tried to call best price on, say, 30? Now we saw before with brute force, we ran out of memory. So what happens for our recursive solution? So the problem is that why is it so slow, right? This is I thought we're doing dynamic programming. It's meant to be quick. We're meant to take exponential problems and make them quadratic. So why is it so slow? We did 20 before and it was pretty quick, but then we just do another 10, right? Not even double it, and it seems like it's just taking an eternity. And it turns out this is the case. So I'm just going to stop this here, right? It turns out that we're missing a key ingredient to dynamic programming at this point. And that is that dynamic programming loves caching. And right now we're not caching the results, right? And if we kind of cast our minds back to the Fibonacci sequence, when we tried to implement the Fibonacci sequence, we saw we kind of had this call graph, right? The Fibonacci of 5 had to call a Fibonacci of 3 and Fibonacci of 4, which had to call Fibonacci of 1. And we kind of built this call graph. And we saw that we kind of did a lot more work than we needed to. Just, when we just kind of had our recursive definition, right, we're doing a lot more work than we had to. We were repeating work. And then here we're saying, like, we're repeating, calling a Fibonacci of 2. We kind of call Fibonacci of 3 times. And so we're doing the exact same thing here. And we're not using caching. So what we really need to do is we want to say, okay, cool, great. You've got your recursive definition, but now you want to try and cache some intermediate results. And so what I've done is I'm basically taking the example we have for Fibonacci, and I've basically defined what the call graph would look like for dynamic, and I think we've called this now best price. So imagine our function f of n is called, our best price function is called f of n, and we can see to compute the best price for rod length of 4, all right, and we'll say rod length equals n. So we can see here that to compute the best price for a rod length of n, in this case when n equals 4, we've got to go call, like, okay, cool, we've got to go call, so we check the price for 1, but then we have to say, all right, well, give me the best price for 3, right? I need the best price of 3 and 2 and 1 and 0, and I'll take the max of that. But to call the best price of 3, I've got to call the best price of 2 and 1 and 0 and take the max of that. But then to us to call 1, and we can see that, look how many times we're calling f of 1 and f of 0. And then look how many times we call f of 2. We call it here, here, anywhere else? No. But all these nodes, right, are more work than we need to, right? We only need to call f of 0 once, or f of 1 once, or f of 2 once. Once we do it once, we can reuse that result, right? And this is the idea of caching. That right now it's when we call our best price function with 30, the reason it's taking so long is because it has to do all these recursive calls, and it's doing the recursive calls and it's repeating work that it's already done. And so what we would like to do is we would like to say, well, after you compute f of 0, cache that result, right? And so we want to replace, just like we had for Fibonacci, right? We want to use memoization, right? And what we want to do is, and I think I have an example here. I might be just here. So if we kind of think of our case here where f of n is the best price for a given rod length, right? We want to replace all those, instances where we repeat the work with a cache version, just like we did Fibonacci. So what we're going to do is we're going to define so here I've got this utility function called, somewhere, called Memo. And Memo, right, is like a decorator, right? It takes a function as an argument and it returns a function. And all it does is it just wraps this function in a cache, such that it looks at its first argument and it says, if I've seen you in the cache, right, I'm just going to return you. If I haven't seen this argument, if I haven't seen this argument before, I'm going to call the function, right, with the arguments you passed, and then I'm going to cache that result. And then we just have a clear method that essentially just kind of reset the cache such that in between test cases we can clear it out. And so what we're going to do is we're going to define, say, best price 2. Actually, we're going to define it like this. So we're going to say best price 2 is memo of this kind of inside function, if you like. And then we're just going to make sure that the recursive call calls the function that memo returns us. So that's the only change we had to make. You just had to wrap our original function, right, in this memo decorator, and we just have to make sure that our recursive call returns the function that memo returns as opposed to this inner function, right? Because if we call best price instead of best price 2, it would say we would kind of miss the cache, right? Because the function wrapped, the memo wrapped, doesn't have a chance to kind of check the cache. It would just keep calling this internal function. So now we've got best price 2, right? We can say, okay, cool, we've got best price 2, that's good. Let's grab a set of prices. Let's come back here, let's run this. So we saw before that our first attempt, we just had a recursive definition, which was best price, right? When we gave it 30, it just kind of seemed to take forever, and we kind of gave up on it. But now, oh, what's going on? Come on.
A, you didn't reply to my text.
Oh, so you text me.
And B, I went to that place and...
Which one will I answer? Oh. Yeah, have you had lunch?
Have you had... Yeah, no, have you?
No.
We don't know what he's doing.
That's a constant. Come on. Oh, what? No Wi-Fi. So painful. All right, so we're gonna grab. All right, so we're gonna grab. So we ran before our best price one on 30, and we saw it just kind of took forever, right? So now we're gonna try the same thing. But this time we're going to cache results and see what we get. And we get best price 2 is not defined. And that's because, why? That's because const best price 2. Need to run this maybe. All right, so we're going to call best price 2 and I'm going to quickly grab some prices. Whoa, look at that. So 30 just, when we didn't cache, it just took forever and ever and ever. But now we have best price 2, which we can see that best price 2, right, where we've kind of cached, these intermediate results, it was almost instant. And we could kind of do the same thing for, I'm just going to define EG price or something, which is just going to be like that, just so I don't have to keep copying and pasting. EG price. So we saw that was like almost instant. What about for 60 with our example price? 120. So best price 2, and then I'm going to say 200 with our example price. So we can just see the power of caching here. That once, all right, we've got our recursive definition. When we start caching it, we can compute things really quickly, right? We're talking. I think in this case we're talking in the linear time. I think we're in linear at this point because we just, if you give me n, I just got to go from, maybe actually not linear. Maybe we're talking n squared. But anywho, the kind of really cool thing here is that, that we can do this. Before we couldn't. But then we kind of think, well, where's the limit? What if I said, I have a rod length of 2,000? Or a rod length of what else? 20,000. JavaScript heap ran out of memory. So it looks like what's happened is we had a Stack Overflow, right? We've kind of, I know it's saying heap our memory and not Stack Overflow, and it might actually just be that it's ran out of out of memory to solve the kind of intermediate results, but I think this looks a little bit like a stack. I mean, what's caused this issue is because while we don't need to, while we can store the results, we're still doing this recursion, right? We're still recursing, right? We're just recursing less. We're doing less work, but we're still recursing. But give me a big enough rod, right? I'll call the stack overflow, because if every time I recurse, I have to create a stack, and eventually I've got so many, recursive calls that will be overflow. So we're not quite home yet, right? It'd be great if there was some way that we could remove the need to do recursion. And if we remember for Fibonacci, right, there was this way. There was a way that we could kind of eliminate the need to do recursion. And if we kind of look back at our kind of call graph, our call tree, right? So, F here is 4, but imagine in that 20,000 example, even though we're caching nodes, we still have to go quite deep of recursive calls, right, to get to the kind of root, to get to one of these root nodes, or these leaf nodes rather. And so what we can do is, if we notice, right, so this is kind of, one part of, we get to this point, we're like, cool, we've got a recursive definition, we've thrown some caching at it, that's pretty good. It's a lot better than the brute force. But the way to make this, the way to go from this recursive definition to an iterative definition is to notice that we can kind of almost work out what are the dependencies, right? For F2 to compute, we can say that it needs F1 and F0. And for F3, we know that, for F3 to get return a value, it needs F2, F1, F0 to return a value. So you can almost look at this tree as like a dependency graph. These arrows tell you what nodes have to complete before you can complete. And so if we do a pre-order traversal, that is just to say, if we walk over this kind of call, this tree, where we make sure that we visit our children before we visit ourselves, something interesting would happen. So if we kind of start with the left-hand side, we would get f of 0, and then we can walk up to f of 1. And then f of 2 says, well, I can't finish until I visit my child, so it would then call, wouldn't do that, f of 0. And f of 2 says, cool, I've seen all my children, so I can now, I can now be, I can return. And then F3 says, well, F2, that's good, F2, you've finished, but I still need f of 1 and f of 0 to finish. And we can say f of 1 calls f of 0, and then we go up to f of 0. And then f of 3 is like, all right, great, f of 2, f of 1, f of 0, they're all finished. Hey, I'm finished as well. And then f of 4 comes up, right, and says, well, only f of 3 is finished, so I still need to go and do all this work, right, before I can return. And so if I quickly just do the traversal, right, we go straight down to the root, we come up to f of 1, we can't do f of 2, so we have to go over to f of 0, then we can finally do f of 2, and then f of 4 says, well, I still need f of 1 says f of 0, it's a mouthful, and eventually f of 4 says, great, everything else is done, I can finally do my job. So this is kind of, we're all right, what have we got here? And we kind of saw before that we know we're not doing all this work. So we know that anytime we repeat a node, we're just using the cache as opposed to making a recursive call. So we know that, in this case, this is just using the cache, right? And f of 1 here, that's also using the cache because we've already computed f of 1 previously. And then this is also the cache. And we can say this must be using the cache. And this is using the cache. And so I'm just going to go through and replace all the nodes or recursive calls with their cache counterpart, cache at 2. And so you can see like, all right, well, gee, we're replacing a lot. And that kind of makes sense because as you kind of go further onto the tree, you would expect that you're not doing any more new work than f of 4. So we kind of have this traversal here, right, where we call f of 0, right? So first thing we do is call f of 0. Then we call f of 1, right? But then instead of calling f of 0 again, we just reuse the fact that we've already called f of 0. So we use the cached value for 0. And then we go to f of 2, right? And so we know the cached, the cached calls, if you like, they don't cause any recursion. So we're kind of like, we're free to remove them from our sorting, our list here. So cached, you're gone. Off you go, cache. And so we're getting a lot simpler, which is nice. And all we're left with is f of 0, 1, 2, 3, 4. That's strange. So once you remove all the cache calls, you can see that we call f of 0, and then we call f of 1, f of 2, f of 3, and 4, and it looks just like Fibonacci. We saw for Fibonacci that if you did the same process, right, you kind of saw the fact that if you did the exact same process, we traversed, did a pre-order traversal, got rid of the cache nodes, we could reverse the base nodes. We saw that we kind of had the exact same thing, that we're moving from 0 to 5, right? That we could first compute f of 0 and then move on to f of 1 and use that result. That's kind of the dependency. So we've kind of resolved this dependency and it looks very similar to Fibonacci. But how do we take this and actually make it iterative? Like what this is saying is that if you call f of 0 first, and f of 1, f of 2, like if you call f of 0 first, then you can call f of 1 because f of 1 needs the result from f of 0. And to call f of 2, right, to call f of 2, you need to first call f of 0 and f of 1. And so we can just have like a loop that starts at 0, right, iterates up to 4, and just stores each result. And you know that once you get to 2, you've already computed 0 and 1 by the fact that you've started from 0 and iterated to 4. So we're kind of getting very close now, right? So we're going to have our third attempt, and might be probably our last attempt, at implementing best price, and we're going to call it iter for the iterative version. And we're going to take the same thing on rod length and prices. And we saw here that the idea is that we're going to basically iterate. So, yeah, okay, let's say that. We're going to say for I equals 0, I is less than rod length. That's not how you spell rod length. While I is less than rod length, less than or equal to, we're going to increment I. Right, and we're going to, instead of wrapping this in a cache, we're going to have something called the cache, which actually will be an object. And we think about so we're kind of here, right? And we've got to return something, right? We've got to return from the cache. But if we just think about moving from 0 to 1 to 2 to 3, right? So we want to do the same thing, right? Effectively, the structure's the same. We want to say, okay, if we take, here we saw there was a base case. Let's kind of first translate our base case. So the base case for best price 2, right, the recursive version just said like, okay, cool. If it's 0, return 0. So let's have that, right? If the rod length is 0, return 0. And then that way, we'll start iterating at 1, such that we'll just return cache at rod length. Right? So if you call best price iter with 0, it'll say, okay, sweet. It's not going to go into this for loop because I will be 1, so 1 will not be less than or equal to 0, and it'll just return whatever is at 0, and we can see whatever's at 0 is 0. So that kind of looks like the base case is covered. But now we've got to kind of translate this case, which is a little bit trickier. but it's kind of the same idea, right? We're going to do the exact same thing. And what we're going to do is we're going to say, all right, actually I won't comment that out. I'll keep that as is. That. So const range. I might just throw map onto the next line. And so in this case, we had return math.max, right? So what we're going to say is, instead of best price 2, right, you think, well, you're just going to call it. So this would be the same before, we'll just call it iteratively. So we're just going to call it recursively. But we're just going to replace every recursive call with just saying, can you just use the value from the cache? And we don't need prices because it's not a call, right? And so now we're just going to directly say, well, instead of recursively calling it, you must have this value because rod length minus I is going to be whatever the current rod length is minus I starting at 1 up to rod length. So it's going to be, it's going to be bounded below rod length. Well, yeah, below I rather. So we're going to replace that. And we can say, instead of 1, okay, yeah, let me kind of start that again. So how do we know that cache will have a value when rod length minus I is called, right? Because rod length could be, 10, and I would be 1 to start with. So this will be rod length 9, and it'll say, all right, what's the cache of 9? You go, well, you haven't seen it yet. So what we're actually going to say is we're going to bound it, right, from. You want to the idea of what we're doing here is instead of top down thinking you give me a rod length of 4 and I'm going to break up into 1 and then what can you get for 3 and then 2 and then what can you get for 2 and then 3 and then what can you get for 1. I'm going to build up. I'm going to say, all right, look, I'm going to start with a rod length of 1 and then I'm going to add on, right? What's like the best that I'm going to add on 1 and then I'm going to add on another 1. I'm going to add another 1, and I'm going to kind of build up until I get a rod length of the size that you're after, right? So this is kind of what this, I going from 1 to rod length represents, kind of building up the size of the rod. Which means we don't want 1 to rod length, we actually want 1 to I, right? So in the case where the rod length is 1, we just want to check where the rod length is 1, right? And then when rod length is 4, we want to go from, 1 to 4. And so I'm going to call, let's change this a little bit. Let's rename I to n. And so you only go up to 1 to n. And we don't want to use rod length because the rod length now will change depending where we are in the for loop. We start with a rod length of 1, then we go to, in the next iteration, we have a rod length of 2. And so rod length really is n here, right? It kind of starts from 1 and goes to rod length. And so we now know that n minus I will always be less than n, right? That's how we know that there must be a value for the cache. If n is 4, then I is going to be 1 to n. 1 to 4, right? So it'll be cache, we'll say, what's the cache for 3, then 2, then 1, then 0. So we know that it must be all the cache values beforehand. And so instead of returning, we're just going to set the cache for n. And so now that's it. I mean, we can kind of remove this. That's the, it's kind of funny here. This is the iterative version. It kind of, if you kind of squint and you look at the best price to, this recursive version with the memo versus the iterative version, they kind of structurally look the same, but we're now removing this kind of overhead of the recursive call. So let's see if that works. So if you kind of come down to run tests, let's replace best price with our iterative version. And let's run that. And it says, I don't know what the hell you're doing. And I say, cache at n. What did it say? $82, where are you? It says, I don't know what you're doing here. Fair enough, kill that. All right, second time's a charm. All right, no syntax errors. So we're gonna now run, or if this works, if we're allowed to. Okay, so we're gonna run tests. So now we're gonna compare our, actually we don't want to, we know our brute force is, well, sure, let's compare to our brute force. So brute force was 8, the iterative version was 8. 6 and 6, 4 and 4, 22 and 22, and 24 and 24. So it looks like we're getting the same results as the brute force solution. So we're kind of there, we've done it. We've got our iterative version, and that's pretty good. So if we kind of look before, I think we said that with best price, with our recursive version using caching, I think we can get to 2,000 for the rod length and it would overflow. But now if we look at, 20,000 with our example price, we'll see, in this case, we won't get a stack overflow. We'll actually get a result. Now, it might take a little bit because, we've still got to do, almost n squared. This is quadratic. It's not linear. It's not. God, you love this. If this was, log n, that'd be great. But let's see what happens. Cool, we get a result. So last time we saw that that we got a stack overflow for our best price 2, or was it 2 or 3? I can't remember now. But the recursive version, and now we say we get a result. So we kind of started here at brute force, all right, which had a running time of 2 to the n, right? And then we kind of ended with this kind of iterative version with a time of n squared, but a little trick. So that's I hope that kind of gave you a sense for how do you go about solving problems using dynamic programming, and where do you start, how do you go from recursive to iterative, and kind of how do you think about these problems. And I think it always comes back to the first thing is what's the solution space? Can you implement a brute force solution first? And then once you've got that, can you define a recursive solution? And then once you've got the recursive solution, you slap some caching on there. And then, only then it's kind of easier to think about how to go from that, memoized version to an iterative version. So I hope this helped. Way longer than I kind of completely failed the 30-minute challenge. But I hope this was useful. All right. Thank you.